This lecture covers a review of linear systems developed during the Intro to Circuits and Electronics course, EMP 231. And in this review, we're going to refresh on differential equation description of a system. How to derive or arrive at a characteristic equation from the differential equation, and how to use that to arrive at the natural response of the system, natural, homogeneous, complementary, that sort of thing. We'll refresh on transfer function representation of a system, and we'll synthesize that. So we'll look at both the synthesis from the differential equations, but then we'll also use impedance. Remember that became a much simpler tool, more expedient to use impedance. And then we will talk about transfer function interpretation. In other words, interpretation. Specifically, we can use the transfer function to determine the natural or homogeneous response, and we can find the steady state response to sinusoidal excitation. So we'll review all those, and that will prepare us for some new material in a subsequent lecture, which will deal with how do we use the transfer function to plot how the system's response as a function of frequency. So we'll look at frequency response. So eventually, next, we'll talk about frequency response plots and the techniques for doing that, making approximate plots by hand expediently. Okay, differential equation description. So, in order to write the description of a system as a differential equation, we have to use some conservation laws. And in electric circuits, that was KCL, which was conservation of charge, and KVL, which was essentially conservation of energy. So KCL, of course, is just the sum of currents in a converging on a node is equal to 0, and KVL is the sum of voltages around a loop is equal to 0. Secondly, we need terminal characteristics for each type of element. So for electric circuits, this was the VI relationships. And so we had our basic elements were resistance, and a voltage VR, a current IR. We had a capacitor C with the current IC and a voltage VC. And we had inductors, inductance L, current IL, voltage VL. Notice that I'm using the passive sign convention. The current, positive current, goes into the positive node. The relationship describing these would be VR is equal to R times IR, or IR is equal to 1 over R VR. VC is equal to 1 over C, the integral of IC dt, or IC is equal to C dVC dt. And VL is equal to L dIL dt, and IL is equal to 1 over L integral of VL dt. We can combine those together to form a differential equation. So here's an example. If we have a voltage source VG driving an RC network, we have R and we have C, we have a voltage VC, and we have a current IR, I'll call that IC. Okay, and if I use this notation that this is VR, that would mean then this current is IR. And we might start, of course this is trivial, but I'm going to nevertheless use KCL explicitly on this. So we're going to write KCL at this node here that I've marked, and we sum the currents leaving. So the currents leaving would be IC leaves, right? So we have current leaving this way, IC, and we have a current that leaves this way, which is minus IR. So we have IC plus minus IR is equal to 0. We can then write IC, assuming that we want to write a differential equation in terms of the capacitor voltage, we can replace IC with the expression for the voltage of the capacitor, that's C dV dt, minus IR. Now IR is equal to VR over R. So we use KCL. We also need to use KVL to complete this. So KVL, if we go around the loop like this, counterclockwise, we'll have minus VG, because I'm going to use the notation or the convention that when I enter a negative node, a negative labeled node, I'm going to say that's a minus. So minus VG plus VR, because I enter the positive node of VR, plus VC is equal to 0. I can write VR then in terms of VG and VC, and I can plug that in up here, which results in C dVC dt minus VG over R minus VC over R is equal to 0. Multiply through by R and bring VG to the other side. And I have this as a, that's a plus right there. Okay, plus VC is equal to VG. This right here is our differential equation that describes how VC, the capacitor voltage, evolves in time. And it's as a function of VG. Of course, it becomes more difficult to solve if VG is changing in time, but nevertheless, we would use this differential equation to solve for VC as a function of time, theoretically for any arbitrary VG signal that excites the system. Now, although this differential equation describes an electric system, it would have the same form if we were describing a first-order mechanical or thermal system, etc. And so we actually can think about for a moment some analog quantities that would be analog to voltage. So if we were talking about a mechanical system, translational, we might have force instead of voltage. If it was rotational, we might have torque. If we had a fluid system, we would use pressure. And if it was some kind of heat system, thermal system, we would have temperature. Okay. All of these can be given a common term, and that is they are all expressions of effort. So think of trying to push the mass to move it. A lot of effort means you apply a lot of force. A little effort is you apply very little force, or very little torque, or very little pressure. The effort is what is the mover behind a response of things moving, okay, or flowing. And so electrically, what flows is we have current. And current, of course, is coulombs per second. Mechanically, translationally, we would have velocity, meters per second. If it was a rotational system, we would have angular frequency, so something like radians per second. If it was fluid, we'd have flow, which could be a volumetric flow rate, so something like meters cubed per second. You can also have mass, volumetric flow, and then mass flow, which would be in terms of some mass, kilograms per second. And then if it was a thermal system, we would have heat flow, which would be joules per second or watts. All right? So if there's a temperature differential across some member, you have heat that flows. All of these are referred to as of flow. So we have effort and we have flow. And that'll help us to think more generally when we write, for instance, a first-order differential equation. We could rewrite this differential equation as tau times d dt of effort, right, plus effort is equal to some forcing effort. And we'll see that when we talk about some of these other domains, these same differential equations will show up time and time again. All right, so now we have a differential equation. What can we do with it? Well, we can use the differential equation to find the natural and the forced response of the system. Again, some other terms. Natural would be homogeneous, complementary, and you could say transient. For the forced, we would say particular solution, or the steady state solution. There's probably some other terms I'm not thinking of right now. So you can find both of those. To find the natural response, or natural homogeneous response, we need to use the homogeneous differential equation. So, given our system from our example, we have RC, which I'm going to call tau, times the derivative of the capacitor voltage plus the capacitor voltage is equal to Vg. The homogeneous differential equation is the same differential equation but with the right side set to 0. What is the significance of that? Well, remember, this is describing this RC, and what it does is it sets a 0-volt excitation. In other words, no external energy source. So whatever happens is going to happen because of the internal energies that were in the system when it first started off or when it was released. And the homogeneous equation will describe how that energy will essentially dissipate. So we are using, or we say for the type of equations that we're dealing with, which are ordinary linear differential equations. Okay, the solution is always of the form e to the st, right? Because the derivative of e to the st is s times e to the st, and so you get the same functional form back. So when you have to add a derivative of x with x, an e to the st type function is able to add those two quantities and arrive at something that is equal to 0. So we can plug this in, we can try it, and so I'll have tau times the derivative of e to the st. So let's plug in e to the st as a solution. All right. In fact, let's call it VO times e to the st. I want to assume that's my assumed solution for VC. So we'll say try VC. I'll say H, VC of H for homogeneous. So when we plug that in, we'll take the derivative, we'll get S VO e to the st plus VO e to the st is equal to 0. We can pull out the VO e to the st, and this is equal to 0. Of course, this is our assumed solution. And for this VO e to the st to be a solution of this differential equation, this quantity right here in parentheses must be equal to 0. Therefore, tau times s plus 1 equals 0 is what we call the characteristic equation of the differential equation tau Vc dot plus Vc is equal to 0. Therefore, the homogeneous solution is of the form some constant times e to the st, where s is equal to, well, what is it equal to? We don't know yet, but we do know that tau s plus 1 is equal to 0. So that means that s is equal to minus 1 over tau. Okay? In other words, the homogeneous solution is e to the minus t over tau. This is for t greater than or equal to 0. Plot that. Starts out at v naught and exponentially decays. Okay, at t equal to 4 tau, recall that e to the minus 4 is approximately 0.02. Okay, so in other words, it's 2%. So at 4 tau here, this would be at approximately 2% of whatever it started off at. So recapping, we see that if we use effort, flow, relationships, plus conservation laws, we take these, we can combine those to arrive at a differential equation. We can then go from the differential equation to the characteristic equation, and from there we can arrive through the roots of the characteristic equation, we arrive at the homogeneous solution. And this is general for any domain, any differential equation that represents any physical or even non-physical system. So as an example, suppose a system has the following differential equation. Y double dot plus 3y dot plus 2y is equal to 0. The way we arrive at the characteristic equation is, and let me go back and point this out over here, if I write the differential equation as tau dvc dt plus vc is equal to 0, and then I write the characteristic equation as tau s plus 1 is equal to 0, we see that tau and the 1 here are preserved, and I have this mapping between the derivative of vc and s and vc and 1. So that's how I get from my differential equation to my characteristic equation. So down here, the second derivative of y will turn into s squared plus 3s plus 2 is equal to 0. Now this can be factored into s plus 1 times s plus 2. And so the roots of this characteristic equation are 1, minus 1, and minus 2. Therefore, the homogeneous solution has the form, I'll call it y01 e to the minus 1t plus y02 e to the minus 2t. Right, that would be where y01, these are just constants. These are constants that would be determined from initial conditions. So, but in general, this is basically an exponential decay, or an exponent could either be positive or negative depending on the polarity of y01. And this is also an exponential decay, albeit a faster decay, right? Because it's minus 2 times time. So these could equal together. It all depends on initial conditions, but one possibility would be that it could start positive, it could come down and take a little negative dip and then settle up, like that, for instance. Secondly, we can use the differential equation to find the steady state or forced response. Now, we did not take this approach in the circuits course. We did later determine, we did do this for, we did this in P231 for VG equal to a constant. Remember, like if it was 10 volts or something. Right? We solved for the case of sinusoidal excitation, but use the transfer function instead of the differential equation. And that's what we're going to do here as well. Okay? So we did not ever solve for the steady state or the forced or particular response to a sinusoidal excitation using the differential equation. The furthest we went was the forced or steady state response due to a constant voltage Vg. So for instance, if Vg was equal to 10 volts in the current example we're looking at, we find that because this is of the form e to the st, happens to be e to the 0t, right? We claim that the response VO, particular, right, this is the forced response, is going to be of the form some I'll call it VOP of the form e to the 0t, right? So you force it with a constant, we're going to claim that the response is a constant. So then you try it. So we have tau times the derivative of Vc, the particular solution, plus Vc, particular solution, is equal to Vg, which is 10 volts. Well, the derivative of this is going to be 0, right? And VOP times e to the 0, which is 1, is equal to 10. Therefore, VOP is equal to 10. And we have found this is the steady state or forced response due to Vg equal to 10 volts. Now we use the differential equation to do that. Now we also expanded this by saying, what if Vg was equal to something of this form? It was 5 volts and then it stepped up to 10 volts. So 5 and then it went up to 10, and it did this at whatever, 3 seconds. All right. You recall how we expressed this? We used the unit step. We said we have 5 volts plus, we're going to add another 5 volts at time 3, so it'll be u of t minus 3, where u of t is equal to 0 for t less than 0 and 1 for t greater than 0. Right? And so we learned that we could actually solve this by really inspection. So we know that Vg equal to 10 volts will lead to Vc particular equal to 10 volts. And Vg equal to 5 volts will lead to a particular response of 5 volts. The only thing we don't know is if Vg goes from 5 volts up to 10 volts, how does the capacitor voltage respond? How does it get from 5 to 10? Well, the way it gets between the two is captured by the natural response. So we found that since VCH, the homogeneous response, is of the form some constant times e to the minus t over tau, okay, we can therefore claim that Vg is going to look, or Vc is going to look like this. So it'll go from 5 up to 10, is at 3 seconds. And this response here is going to be characterized by this e to the minus t over tau. So we can write it just by inspection. We'll say Vc of t is equal to, let's see, at time 3, it's going to be equal to 5 volts. Let's do this. At time infinity, it's going to be 10 volts. I know that, right? But we're going to subtract something so that at t of 3, when t is equal to 3, I will have this quantity here will be equal to 5 volts at t is equal to 3 seconds, right? I need to satisfy that. So how do I get this quantity to evaluate to 5 at t equal 3? Well, I need to have 5 in here, so I got to write 10 minus 5 times e to the minus t minus 3 over tau. All right. And this is valid for t greater than or equal to 3 seconds. Now, if I want to describe this for all time greater than 0, I would write, let's see. So I could write, it'll be 10 minus 5, e to the minus t minus 3 over tau, as before, and I'm going to multiply this whole thing by u t minus 3. So in other words, this thing is valid. It'll look like this. 0, and then it's going to jump up and do this at 30 seconds. Okay? Plus, I need something that will cover me from 0 up till 3 seconds. So then we'll have 5 times u, well, I would write it this way, 5 times 1 minus u of t minus 3. What does that do? This right here gives me something that looks like this. At 3 it goes from 1 down to 0. Okay? So I put those two together, and I can get VC for all of positive time. Now we can collect this, clean it up a little bit. I'd have 5, and then minus 5 u of t minus 3 can combine with this guy here. So I would have plus 5, actually plus 5 times 1 minus e to the t, e to the minus t minus 3 over tau times u to the t minus 3. Right? So this here is constant. And then this piece here is at 0 up till 3, and then it pops up to, actually no, it starts at 0, and it works its way up to 5. Right? So both these together form the overall response. So we did some of that. So we were able to assemble a couple different segments of constant input forcing, and we used the homogeneous and the particular response from the differential equation to assemble a complete response. But we were restricted to just piecewise constant excitations. Now in a little bit here we'll review steady state or forced response to sinusoidal excitation, but we'll do that after we review our transfer functions.